So today we're going to discuss some basics about statistics. Okay, statistics is a very big subject to in itself, but we are not going to look at every inch and detail of statistics, but only that is necessary for our machine learning purpose. Okay, to start with, statistics has got couple of things, like we have something called as descriptive statistics and also called something called as inferential statistics. So today's session will be all around descriptive statistics. Before I start my session about statistics, I just want to make you understand why we require statistics. Say for example, we have a lot of data with us. Very simple cases, like you go and buy milk every day. Okay, you tend to have some common patterns. So you are buying milk from a common store. Okay, every morning, maybe the guy comes to your home and then he drops the milk to you, and like that he drops the milk to many other houses. Say for example, if he doesn't look at the statistics, he will not be able to know how many milk packets he'll have to procure every day from the company. So statistics in one way or other way, it is required for our daily routine. You use it or you do not use it. Every common man requires it. Okay, even be it a small shopkeeper or be it yourself. Say you maintain stats of your own financials. So if you do not have the proper stats, probably your figures will fail down. Okay, so in one way or other way, we will require statistics so that we can plan in a better way. Okay, so let's start with descriptive statistics. So when I talk about descriptive statistics, we are looking at only one feature. Say for example, you have a data frame. You already know what a data frame is. In data frame, you might be having one continuous column. Let us say age, or let us say height of students, or let us say marks of students. Okay, so when you consider only one feature or one list of values, any inference that you make from that list of values is called as descriptive statistics. Okay, so you can imagine that that any conclusion that you try to make from one particular feature of a data set, that is termed as descriptive statistics. Now, what are the conclusions that you can make? So in the example of milk packets, as I told, the example is he can come up with the total count of milk packets on a given day. Maybe if the he can also include, like, what if the day is Sunday, what if the day is Saturday, what if the day is Monday and all. Or else he can generally tell for a given week, these are the number of milk packets on an average that I will be selling. To this, maybe the shopkeeper can have some percentile, like let's say like up to 2%, I'll keep it extra, so just in case if there are a couple of people who have extra need, they can purchase for me. Maybe 2% or 3% he can add. So you're talking about some average of the total count of milk packets that you have. Okay, so this average, what you call, is a descriptive statistic. Any inference that you make on that one single column is descriptive statistics. Now, there are two types of descriptive statistics that we are going to cover today. One is measure of central tendency, which I already told. One is mean. The other is measures of spread. So I'll tell you what measures of spread is in a moment. But there are two things that we should be looking at. One is central tendency, and another is measure of spread. So when you talk about central tendency, there are a couple of things that you can look at. One is the average, which I already told, and then there is something called as median, and then something called as mode. Okay, so mean in the first case, it is nothing but when you have a data set like this. Say for example, I have a data set like this wherein I know who is the individual. I mark that individual as 1, 2, 3, and so on with 10. And for each individual, I'm going to record what is the weight of that each individual. Say for first person, the weight was 73. For second person, the weight was 65, and so on. For 10th person, the weight was 73. So when you have a series of data, this is a series of data. You can go and calculate the average by summing up all the values, dividing by the total number of count. That is 74. So this is, you call it as mean or average. It is an overall figure that can represent the whole data set. Okay, so on an average, I can tell that the common weight for a given class of people is 74. But wait, when you have data like this, sometimes the mean can be uh, it cannot represent the whole data set in a proper way. Why it cannot represent is, say for example, somebody went and entered a wrong data. So for example, instead of 90, he recorded it as 290. Okay, so what would happen? The number here would completely change. So the inference which you're trying to make will deviate if you have something called as an outlier. I think we already discussed about outliers when we saw about box plot. Okay, when we have a box plot like this, there was a graph of this kind. So we called this as Q1. This was Q3. This was the median or the average and interquartile range. Okay, so whenever there is a outlier, you would notice that some dots are above or below the whiskers. Okay, this is called as an outlier. So one common thing that to look at is mean will drift if there is an outlier. Just keep that in mind. Okay, why I'm telling this is because average was the first thing that we generally use when we generally look at a common person who doesn't know about outliers will generally look at mean. So what to look at if there is an outlier in the data set due to some reason? It can be a genuine reason, or it can be a typographical error. If there is an outlier, what should we look at if not mean? Then there is something called as median. Now, what is median? Okay, so you have this data set. This data set, what you'll try to do is you'll try to uh, arrange it in an increasing order, or you can also arrange it in decreasing order. So when I try to arrange it in an increasing order, the values look like this. So this is my lowest value and this is my highest value. Say for example, in the previous case I said it's 290, this can also become 290. So median, if you have like hundreds of values, it is the most centered value. In this case, because we have 10 values, there are two centers, 71 and 73. These are the two centers. And when I have an even number, I should be taking an average of these two centers. So in this case, the median becomes 72. Okay, this I think we have already discussed this in when you were in the school, okay, or maybe in the college. As a common logic. So what we're trying to do is we're simply arranging all the numbers in an increasing order, pick up the most center value. If you have two centers, then take the average of that. Generally, if it is an odd number, you will have only one specific value. If it is an even number, you will have two values, and you will take the average of those two values. And on the other hand, there is something called as mode, which we might not be using most frequently. This is like the most frequent value which is occurring in the data set. So for example, I see 73 here. I see 73 somewhere here also. Okay. So because 73 has occurred twice, the mode of the data set is 73. Generally, on a general note, whenever you have categorical data, at that time when you want to replace the null values, you go with mode. We discussed this point when we when we were doing the pre-processing stage for machine learning. Okay, when it comes to continuous data like this is a continuous data where weight is a continuous value. When you have a continuous data, you should always look at the distribution, look at how the mean and median are placed. Based on the difference between mean and median, you can take a call about whether to go with the mean to replace with null values or to go with median to replace the null values. I'm going to tell you in this today's session how to automate this process. Say you have any data, any continuous column in the data frame, you can write one simple program to look at the distribution, come out with some specific value. It can be a median, or it can be a mean, or it can be some quantile. Based on that, you can come and replace those null values in the continuous data. Okay, let us move ahead. I think this step is very clear. These are all called as measures of central tendency, whether it is mean, median, or mode. It is going to represent one number which is part of a data set, or it is very close to the data set. Okay, keep this in mind. So first thing is mean. One thing to keep in mean is your mean is going to drift quite far away if there is an outlier. Okay. The second step is median, which is the most centric value. And the third is the mode, which is the most occurring value. Okay. Now let's move to the next step. So the next step is about visualizing how the mean looks. Say, for example, we had 10 students and their height was captured. And let us say the height was like this 110, 105, and so on. And one particular person who is at 65. So you can notice the average is around 114.3. This is how the mean looks like. If you want to look at the visual part of mean, this is what the mean looks like. Similarly, if you want to go and have a look at median, this is how the median looks like. Now, in this case, the median is around 119.5 because that's the most centric value. As I said, because we have an even number, there are two centers, and we are going to capture the average of both those center values. So in this case, the median value is 119.5. So if you look at the previous slide, the average was 114. You know how to calculate the average. Similarly, if you want to go and calculate the median, we can use Excel formulas, or you can manually do it. If the data set is small, you can just go and arrange them, or else you can directly use the libraries to calculate the median. In data frame, we use something called as df.describe. So it'll show all the stats for a continuous value. So you can use that to ascertain this. So in this case, the median and mean are somewhat closer to each other. But see, the data is not proper because there are a couple of values which are quite far away from the mean or the median, and couple of values which are also, like in this case, the far, when I say far, it is very less. In this case, when I say far, it is very high. And as I told you about the example of mean, the same data, just the scale is different. You notice the scale here. Okay, the scale here is around 140 to 0. Okay, but when you go to the next slide, it's the same data with a different scale. Now we have 0 to 500. Why we have a different scale is because there is one, maybe a typographical error, which where the height is 450. Maybe the height was 150, but for some reason, say instead of entering 4, the user has entered 4. Instead of entering 1, the user has entered 4. So because of this, you can see what has happened to the mean. The mean has went to 146.2. Previously, it was 114. Okay, previously it was 114, but now it has become 146. So when there is an outlier, mean is easily getting drifted towards based on the outliers. But what happened to median? The median is still at 119.5. So when there are outliers, it is always good to look at the median instead of mean. Or you can treat this outlier. Say, for example, you already know the use case. Say, I go and check back with the source. I have a wrong value. What is the correct value? Maybe it was a data entry problem, and you go to the source and get it corrected. So when you go and come with the correct value of 150, you can get the proper mean. Or else, if you do not have access to go to the source, then you have to go with median value. So these are the general use cases that you are going to come across in day-to-day operations. Like when you have different data sets, probably you might have access to source, or probably you do not have access to the source. So when you do not have access to the source, you have to take a call of what to do with this outlier, whether to delete it or replace it with some value. So maybe you can try it out with different combinations and come out with one possible outcome, and then move forward. So that's about mean and median. Any doubts so far with the central tendency? We'll move forward towards the next thing, something called as measures of spread. So far we have discussed about measures of central tendency, wherein you're always trying to look at the within the data set. Now you're trying to look in a different perspective. Say for example, we have something like this. Okay, we Say, for example, I have a dot. I have a dot here, and I have a circle. Okay. Now, what I want to do is, if I place a dot, I want to look at how far this dot is from this particular center, or this one, or maybe this one, or maybe this one. The dense the dots are. Say, for example, I have a center here. All the dots are around that center. Unlike this, in this case, there are a couple of outlets. Okay. When the dots are at the center, this is more precise data set. And the machine learning can work wonders if you have a data set like this. Okay. It can be more accurate because it knows that it has to be somewhere within that particular center. That is what the whole machine learning revolves. So that is why we keep telling a common word, something called as uniform distribution, uniform normal distribution, or it's something, it follows a bell curve. I'll tell you about bell curve today. But what I want to tell you is how the machine understands is based on this. If all the values are precisely very close to the centric value, the machine learning can easily learn from it. Or if the values are something like this, because this is a real world problem, most likely the real world problem is not as easy as this. Okay, as it is not as easy as this, but it is like scattered, pretty much scattered like this. So when you have so much of scatteredness, it can be vague. When it'll try to balance out each and every dot, it'll try to make a lot of errors. So that is why it'll throw out a lot of error metric. So we'll discuss about what is error metric, but just keep this in mind. The more centric the values are, the better the outcome of the model. Okay. Now, how to measure if the values are centric or scattered? So for that, we have something called a spread. This is measure of spread. Previously, we are talking about data set where we are talking about what is a mean, what is a median, and what is a mode. So mode is the most frequent value, mean is the centric value, and median is the centric value, and mean is just the average. And now we'll discuss something called a spread. How scattered the data is. Just keep in mind, when somebody asks you what is measures of spread, you're going to explain how scattered the data set is, or how far a given value is from the center. These are the two questions that you're going to discuss. So the first thing which we have in measures of spread is something called as range. Now range is very simple. You just look at what is the least value, what is the maximum value. Range is nothing but just the difference between two values. So 90 minus 65, in this case 25, is the range. So if you are given two data sets similarly like this is a weight data set. Say you have one more weight data set. You can compare those two if they belong to the same thing by simply looking at the range. If the range is very common, then you can say, okay, they are somewhat similar, but this is not enough. Just by looking at range, you cannot tell if the two data sets belong to the same population or same data set. Say, for example, I have millions of records for a given weight. I randomly choose 10 samples from that million records, and I again randomly choose 10 samples, and then I want to compare if these two samples belong to the same population or not. Okay, so then you can just go and compare this. You can go and look at range, or maybe you can go and look at quartiles. So what is quartiles? We already discussed something called as median. In median, we told that it is a 50th percentile. So whichever is the most centric value, it is a median. Similarly, you can also have the 25th percentile and a 75th percentile. So you arrange the data set in increasing order. First, get the median value. After getting the median value, you have two halves. One is this and one is this. So in this half, again, you get the centric value. In this half, again, you get the center value. So this one will become the 25th or Q1, and this will become Q3 or 75th. These are called as quartiles because it is dividing the data set into four halves. 1, 2, 3, and 4. And this is Q1, this is Q1, this is Q2, this is Q3. So this becomes the first 25th quantile. This becomes the 25 to 50. This becomes 25 to 75, and this becomes 75 to 100. So what you're trying to do is you're trying to arrange the data set in a increasing order, dividing in four halves. So if you want to divide it in four halves, you'll require three quarters, like four quarters probably. So this whole becomes Q1, this whole becomes Q2, this whole becomes Q3, and this becomes a Q4. You don't have to mention about Q4, it is understood. So you can, after you have the quartiles, you can know in first quartile what is the range, what is my start value and what is my end value. Similarly, for the last quartile, what is my start value and what is my end value, and so on. And the difference between these two, the Q3 value and the Q1 value, is nothing but the interquartile range. So you're just trying to see how spread the data is. So you're just, when you try to arrange it in four quartils, you're just looking at what is the difference between my first quartile and the third quartile. So that difference, as lower the difference is, the better the value is. Okay, the condensed the data is. But again, the value can be anything. In this case, 6 can be a small number. It depends upon what are your values, what are your initial values, and what are your final values. In some cases, maybe 0.05 can also be a big difference. Why? As I told you, the scale is what you should also look at. If you're not looking at scale, if you're looking just at this number, then you might get deviated from the actual inference of what the interquartile range is trying to tell you. Okay, and then this is a very important topic, which we call it as variance and standard deviation. Okay, so we are discussing about measures of spread. We saw what are quartiles. We saw what is range. We saw what is interquartile range. Now, there is something called as variance. So variance is, in simple terms, it is trying to capture the difference from its mean. Say you have the actual value. This is my actual value, and this is my mean. Okay, the mean is, previously we saw the mean was something around 73. So what you'll try to do is you'll try to capture the difference between 65 and 73. You square it up and then you divide by total number of values. Why you're dividing by total number of values is trying to have the variance of the whole data set, not just the value. If you just want to look at the value, maybe you don't have to look at, maybe you don't have to divide by n. Okay, but I want to look at the variance of the whole data set, not just one data point. So I'll calculate the variance of each data point, and then I'll divide it by total number of records, which I'll have something called as sigma square. Variance is denoted by sigma, and we first find the difference of each value from its mean, square it up, and then divide by n to get the sigma value. It is sigma square because you have squared it up. You can also apply a square root to get the standard deviation. So these two are very important, the variance and standard deviation. These are pretty common topics that you're going to look at. So variance and standard deviation is going to tell you how scattered the data is. One simple example I'll tell you, okay? Say, for example, you have a data frame. Just listen to what I'm saying. You have a data frame and you have one column. Say, for example, this is one ID column and all the values are ones. All the values are ones. You can write a program because it's the same value for all the records. It doesn't matter anything to me for my model because I'm not going to make anything from out of this. For any record, it is one. There is no so the mean will be one, the median will be one, the mode will also be one. Agree? Let us say there are 100 ones. So the average will be one, the center point will be one, the mode will be one. Okay. What happens to my standard deviation? 1 minus average 1 will be 0. So my standard deviation and the variance will be 0. Agree or not? 1 minus mean is also 1, 1 minus 1 is 0. So there is no scatteredness in the data. So when you see any such columns where you have variance equal to 0 or the standard deviation is equal to 0, it means that it is not going to impact in any way to your model. Are you with me? There is no variance in the data set. So these columns can be dropped by default. Say, for example, if you're trying to write an automated pre-processing step, and you notice that there are a couple of columns where you do not have any variance in the data, just go and delete it. So how do you validate if there is no variance in the data? Simply go and calculate the variance. So you notice when there is variance is equal to 0 or very close to 0, approximately equal to 0, in that case, you can go and simply delete that column because it's not going to impact your machine learning model. We are using statistics to understand how to help how to use these numbers for our machine learning model. Okay, we don't have to go and read the whole part of statistics, only a basics of it, so that you understand why we are taking couple of additions. Say, for example, you might notice in couple of in cases like we'll go and drop couple of columns, why we are dropping it. So if you want to go dive deep of that why of that question why, then you have to understand all these things. You'll have to understand what is the variance, you'll have to understand what is the standard deviation, what is called as measures of spread.
ఇదంతా ప్రీ ప్రాసెసింగ్ లోనే వస్తుంది కదా.
Correct, this is all part of pre-processing. Correct. Okay. So when you have variance equal to 0 or standard deviation is equal to 0, it is means that the whole column is having a constant value. You can simply go and drop it. You can also drop it if the value is very close to 0, 0.01, 0.05. There is no standard deviation at all. Like it is very, very dense at one particular value. Okay. Just keep that in mind. Okay. Now what we'll do is we'll try to look at what is normal distribution. So far we have discussed about uh, inferential statistics, like descriptive statistics, right? In descriptive statistics, we saw two parts. One was the measures of spread and measures of central tendency. When I talk about measures of central tendency, it is all discussing about the centric values of the data, like what is a mean, what is a median, what is a mode. And when you talk about measures of spread, it is looking at how scattered the data is, like how they are placed within from the center. Similarly, we have something called as normal distribution. This is one more way of looking at our data. What happens in a normal distribution is, first, before you understand normal distribution, we should also discuss something called as z-score or z-statistic. What it tells is you go and subtract each data point from its mean and divide by the variance. This is called a z-statistic. Okay, I'll discuss this z-statistic, like you have the formula here. I'll discuss this z-statistic again when we are trying to talk about standard scalar in the machine learning model. Okay, when we are trying to do the pre-processing, we have completed pre-processing to some extent, but we have more features to it, like you have to convert them to standard scalar or convert the categorical data to one hot vectors. So we'll discuss all that part. So for now, let us understand that there is something called as z statistic, wherein you try to convert the whole series to z statistic series. You're just converting to a different scale. Okay, and when you try to do this, you will have the values from -3 to +3. Okay, and when you look at the data, there are a couple of things that we have to notice. All the data, if the data is having 68% within 1 sigma, this is statistic. Okay, this is 1 sigma, -1 sigma, and +1 sigma. Generally, when you convert to z statistic, the mean becomes 0. The mean and the median become 0. Okay, that is why it is called as -1, and this will be +1. If your data is normally distributed, you account that 68% of the data is within 1 sigma from the mean. What is my mean? As I said, my mean is at 0, and when I say 1 sigma, it is -1 sigma and +1 sigma, one standard deviation away. So when I move one standard deviation away, 68% of the data should be within my that 1 sigma or one standard deviation way. And if you look at 2 standard deviations away, you should account for 95% of the data. And when you move at 3 standard deviation, you should account for 99% of the standard deviation. When you have data set like this, it is called as uniform distribution, distributed data. Most of the cases, you do not have this uniform distributed data. Okay, if you have the uniform distributed data, your model will be absolutely fine. It'll going to correlate properly, and it'll come up with the values which is more accurate within this data set. We are going to use this uniform distribution again when you're talking about hypothesis, okay, null hypothesis and alternate hypothesis. That's for later point. But for now, if you have to remember what is a normal distribution, you should think that the mean should be at 0, and one standard deviation away I should have the data set like 68% of the data is within one standard deviation, and 95% of the data is within two standard deviation, and 99% data is within three standard deviation. This is what you should have. This is called as an empirical rule. Okay, if you have like this, when the mean is 0, the standard deviation is 1, and the empirical rule is followed, then you can term that data as a normal distributed data. Any doubts so far?
No, fine.
Okay, so what happens when there is a difference in standard deviation or variance? Say if your variance is like the what you see in the red color, this is normally distributed. The red color plot is normally distributed. When the variance is drifted away from 1, what happens if it is 0.2? So you will have a peak. This is 0.2. The values are more centered. Okay, and what happens if the variance is around 5? The values are totally spread. So higher the variance, higher the scatteredness. Lower the variance, lower the scatteredness. So for us, 1 is very good. 0.2 is also very good, but you can say that the peak is pretty high. Okay. In this case, maybe the variance is not too high. 0.2 is very less variance. Anything less than 1 variance is very good, but variance of 0 is not good. Just keep that in mind. Just one thing to keep in mind is whenever you want to look at the distribution, you can also look at directly without having to converting the z scores. You just have to notice the bell curve, and the bell curve is how you represent is like the mean and median should be as close as possible. If the mean and median are very close to each other, then I think the data set can be treated as almost normal. It cannot be as exact as this. Okay, this might not what you see in the real world thing. But if you notice that the mean and the median is very close to each other, and your variance is less than 1, then you can say that the data set is normally distributed. There are many cases when the data is not normally distributed, so we will have to treat it like handling the outliers, capping the outliers, or you know uh, replacing a couple of values with some the median value, and then we can convert that to almost normally distributed. I think we'll do that in our pre-processing step. I'll tell you how to do that. But looking at this, if if you were given two data sets, okay, let us say this is also weight and this is also weight, and you were asked like whether these two belong to the same population. So this is a very common term about sample and population. We are going to discuss about inferential statistics. When we go to inferential statistics, I'll tell you what is a population and what is a sample. But say for example, if you have two data sets like this, and the ask was to compare whether these two data sets belong to the same population or not. Okay, you can imagine population is something wherein you have a lot of data and you're taking some samples out of it. And now in this case, the population can be as simple as weight of all 10th class students in a given school, or maybe 10th class students of all the schools within a small region. That is a population. It's like a corpus. In that corpus, you're taking two samples, and you want to check whether these two samples really belong to the same population or not. How do you do that? You can look at the measures of spread again. Okay, it's a common thing. You will have to look at the measures of spread. Now there are a lot of libraries which can help you out to do this, but one common inference or intuition that you have to keep in mind is that with if the population, I mean, if the samples belong to the same population, they should have a similar measures of spread, meaning it should have a similar variance, similar mean, similar median, and so on. If they are very similar to each other, then you can say that they are two where the two samples or two data sets are belonging to the same population. We'll discuss this again when we are going to inferential statistics. Uh, and there is something else that you should also keep in mind. What what you call as QQ plot or quartile plot. So, if for example you have data set one, data set two, we discussed about quartile range Q1, Q2, and Q3, right? If the two data sets are from the same population, their quartiles should also be similar. We have something called as QQ plot, quartile plot. I will tell you when we are going to linear regression, but this is the basic step. When you have similar data sets, then you should have similar quartiles for the both the data set. If you see that the quartiles are not matching, then you can tell that there is definitely some difference between the data set one and data set two. Okay, we'll dive deep when we go to the right topic, but for now just keep this in mind that we should look at measures of spread when you are comparing two different data sets. So if your ask was to compare two data sets and say if they really belong to the same sample or not, first thing that you should get in your mind is look at the measures of quartile. Okay, so the last slide which we are going to talk about today is
సిమిలర్ డేటా సెట్స్ అంటే ఇప్పుడు నీ ప్రకారంగా ఇప్పుడు స్టూడెంట్స్ గురించి అంటే స్టూడెంట్స్ డేటా సెట్స్ అంటేనా
correct.
లేదా కంటిన్యూస్ కేటగిరీ లాగా
No. It should both be continuous, of course. Students అంటే స్టూడెంట్స్ ఉండాలి. But let us say one sample.
నువ్వు కాలమ్స్ ను కూడా కంపేర్ చేస్తున్నావు కదా డేటా ఫర్ ఎగ్జాంపుల్ డేటా సెట్ 1 లో 10 కాలమ్స్ ఉంటాయి. సో దాంట్లో మన టార్గెట్ కాలం తీసేస్తే మిగిలిన 9 అనేటి కంటిన్యూస్ అనుకో.
ఓకే.
సో ఇంకొక
అలా
దాంట్లో
చేయకూడదు. యు షుడ్ కాలమ్ టు కాలమ్ చేయాలి. అంటే ఇప్పుడు వెన్ యూఆర్ టాకింగ్ అబౌట్ స్టాటిస్టిక్స్ కదా, నేను చెప్పే శాంపుల్
కాలమ్ నేమ్స్ మ్యాచ్ అవ్వాలి కదా.
ఫస్ట్ కాలమ్ నేమ్స్ మ్యాచ్ అవ్వాలి ఫర్ షూర్. కాలమ్స్ మ్యాచ్ అయినంత మాత్రాన ఇట్ డజంట్ మీన్ దట్ దే బిలాంగ్ టు ద సేమ్ పాపులేషన్. ఐ సే ఫర్ ఎగ్జాంపుల్ ఐ హావ్ వెయిట్ ఇన్ 2 data frames. Okay, now I want to check whether this weights here and this weights here are same or not, or are similar from the same population. Say for example this is weight of 10th class students and this is weight of 6th class students. Both are weights. I cannot tell that both are same. They're not similar, right? This is for 10th class and this is for 6th class. So how to trust your data is by looking at all these characters. Look at the measures of spread, look at the central tendencies. If they are very similar to each other, then you can tell, okay, they really belong to 10th class students. It's not 6th class students. So for example, if you are for a training data set, you are giving the 10th class data, but on your test data set, you are giving that 6th class data.
ప్రతి కాలం ని మనము చూసుకోవాల్సిందే అలా.
Correct. Individual column, take 2 individual columns, look at the measures of spread, and then only then you can ascertain that they belong to the same population. Why I am saying all the
match అయిన కాలమ్స్ నేమ్స్ మ్యాచ్ రెండు డేటా సెట్ నుంచి తీసుకోవాలి.
కరెక్ట్, సరిపోదు. కాలమ్ నేమ్స్ మ్యాచ్ అయిన మాత్రం ఇట్ సరిపోదు. సో why I am telling all this is because, say for example, you have your training, you have taken one data frame. Okay, you split this data frame into 2 halves. One is for your training and one is for your validation. You notice that your model is pretty good in this data set. Okay, your model accuracy is say 85% or 80%. But when it comes to unseen data, your model is completely nowhere close to this 85%. Nowhere close. Maybe it is around 45% or 50%. So before you go and test it with this data set, you just have to see whether this test sample belongs to the same population or not. If it is not from the same population, it means that your model is not going to work out. Okay, as simple as that. Just keep this in mind. Whenever your model is pretty robust on your test data, on your trained data, it has to have a similar inference on your unseen data. If it is not working on your unseen data, first you have to check whether the unseen data is really from the same population or not. If it is not from the same population, then there is something really wrong. Okay, you cannot say that the model is going to work on the unseen data. You cannot do that. Say for example, my data set or my model is trained on some US data. Okay, the patterns of US is completely different from the patterns of Asian. So the model which is working very well on US data set, I cannot use the same model from Asian data set. It'll not work. Obviously, it'll not work because it is looking for those patterns and it'll try to judge on those patterns. And if those patterns are not available in the Asian data set, obviously it'll not work, right? So you have to make sure that the population is correct. The test sample is from the same population on which the model was trained. So that is why we require the statistic. We have to understand what is variance. We have to understand what is measures of central tendency, what is measures of spread. If you do not understand all this, obviously you're not going to relate why the model is not working. Okay, let's go a little step ahead. Like we saw what is normal distribution. uh, the key takeaways: the mean and median should be closer to zero, and your variance should be as close as possible to one. In this case, the red color one is the one which is normally distributed. If your data set is something like this, it is okay. But if your data set is something like the orange color one or the green color one, then you will have to tune it. You will have to tune the data set in such a way that it becomes closer to the normally distributed scatteredness. Okay. All right. Let's go to one more step, which is how to know whether my data set is normally distributed. Now, I cannot go and plot every time and see. Say, for example, I have a code which is running in the backend. Okay, and I don't get any visuals, and based on the visuals I cannot take calls. I have to automate it. So how to automate this? So for that we have something called as skewness and kurtosis. So skewness is one kind of a measure to tell how symmetric the data set is. Okay, if my data set is perfectly normal, if I say perfectly normal, it is completely evenly distributed. So the data on the left and the data on the right are forming a bell curve. Okay, in most of the cases you'll not have the symmetry. So if you have a skewness closer to zero, as close as possible to zero, then you can tell that it is almost normal. It is not exactly normal, but it is almost normal. So what happens if the skewness is greater than 0.05? It means that there is unsymmetry in the data. Then you'll end up with data set like this, negatively skewed or left skewed, or a data set like this, right skewed or positively skewed. So by measuring the skewness, I can use a stats model in Python, stats.skewness, and I can pass the data set to it, and it'll come up with some value. That internally what it is trying to do is it is just looking at it is going to arrange all your data in increasing order. It is going to measure how many values are on the left of the mean and how many values on the right of the mean. If they are almost similar, then the skewness will be very close to zero. If it is not close to zero, let us say if it is greater than 0.5 or greater than 1, it means that you're ending up with this or this. Negatively skewed. When I say negatively skewed, just keep this in mind. This is a very important topic. When I say it is negatively skewed, most of the data is present on the right part of the data set. The peaks are on the right side and you have a tail on the left side. Negative skewed. The skewness is towards the left, the data is towards on the right. When I talk about positive skewness, the data is on the left and the tail is on towards the right. This is the tail. You notice the tail. You have a never-ending tail on this side. This is another way of looking at outliers. So you have outliers here, you have outliers here. All on the outside is outliers. All on the left side is outliers. By measuring the skewness of your continuous column, you can tell whether it is almost normal or not. If it is not almost normal, then you should be looking at the median value. If it is almost normal, then you should be looking at the mean value. See how the mean is drifted. If it is negatively skewed, the mean is on the left of the median. If it is positively skewed, the mean is on the right side of the median. Why I'm telling this? Say you have null values in your continuous data. Okay, say 5% or 10% of the data is null values. And you have to come up with an automated program which will help you replace all the null values. If you're going by line, you can, okay, you can just look at the graph. Okay, based on the graph, I can tell, okay, if it is because it is a normally distributed, I'll go with the mean. But let us say I should not look at graph. I have to write a program which is going to help me understand whether the data is symmetrical or not. Based on the symmetricity, I should replace the values with mean, or I should replace the values with median. So what I'll do, I'll just go and measure the skewness. If the skewness is less than, let us say, the modulus of skewness, I don't want to look at the sign. If the modulus of skewness is less than 0.05 or less than 5, for example, then I can tell, like, it is almost normal. So I'll go and replace with mean. All the null values will be replaced with mean. If it is greater than 0.5, in this case, I'll go and replace with the median value. You have to understand the part of skewness if you have to go and replace the null values in the continuous value. So tomorrow, when I'm going to replace the null values, you should think why I'm doing this. Why not mean? Why not median? Or why not mode? Look at the skewness and kurtosis to answer those questions. Obviously, you should get that why, because I have to understand why I'm doing this. Okay, you're bound to get null values in the real data. What to do with null values? You can either drop them or you can replace them. If I have to replace them, with what I should replace? Whether I should replace with the mean, or whether I should replace with the mode or median. So if the mean is at the center position, if it is a normally distributed, how to measure if it is normally distributed or not? I have to go and look at the skewness. If the skewness is less than 0.5, I'll go and replace with mean. If the skewness is greater than 0.5, I'll simply go and replace with median. Mode you can forget. As I told, mode you'll generally use it only for categorical data, not for continuous data. Okay, as simple as that. You do not have to do much around this. Just look at the skewness. Based on the value, you try to see if the value is less than 0.5, replace with mean. If the value is greater than 0.5, replace with median. As simple as that. One more thing, which is a common question, is what happens to skewness if the value is greater than 0. If the value is negatively skewed or positively skewed, the data set will behave in a different way. I mean, the data set is already there. The population, the dense, is drifted away from the mean. Now the mean is on the left side for the negatively skewed, and the mean is on the right side for positively skewed. There are outliers. Here also we have outliers. Here also we have outliers. So just keep in mind, if I say left skewed, most of the data is present on the right side and the tail is present on the left side. This is my tail. On the right skewed, the tail is on the right side. The data is present on the left side. Keep that in mind. Okay. And how to position the mean? In the left skewed, mean is on the left of the median. And the right skewed, mean is on the right side of the median. This is very important. Okay. This is very, very important. Probably even if you are going to have questions on the statistics, this is a common thing about explain about skewness. How can you use it for statistic or machine learning problems? This is very important thing. Similarly, kurtosis is also there. I generally do not use kurtosis. I stick with skewness. But if you want to look at kurtosis, it is also going to tell you about positive kurtosis and negative kurtosis. It is going to tell you about tails. Indirectly, both are telling about the same thing. You can stick to skewness if you find skewness is more easy to understand, or else you can go to kurtosis. It is just the measure of how much of tail, where the tail is present. Okay. So in kurtosis, we have a couple of things, like you have three categories of kurtosis. Okay, when you have mesokurtic, platykurtic, and leptokurtic. When you have moderate value, you say it as mesokurtic. When you have very low value, it is platykurtic, and very high value, it is leptokurtic. We just don't have to go in this detail. As I said, you can stick to the skewness. It is telling the same thing, but in a different way. So if you can just, if you want to learn more about kurtosis, we can definitely learn it, but I think it is not required for us. As I told you, like, we can stick with the skewness and we can get the job done. Any doubts so far?
Okay, fine. So far, so good.
Okay, so in the next session, I'm going to tell you about inferential statistics. So we'll discuss about population, we'll discuss about sample, and then we'll discuss about how to estimate the mean and median of the population looking at a sample, and so on. Okay, so we'll discuss about what is central limit theorem and many other things. So we'll have one more session about statistics, and then we can go ahead with machine learning problems like linear regression and logistic regression and so on.